Lesson 4.7 is going to talk about arithmetic sequences, and I hinted at these a little bit and just introduced them very briefly in our previous lesson video. And today we're going to dive deep into the characteristics for arithmetic sequences and what the pattern is and how to use our equation here to predict values further down the line. So let's get started. The first thing is, this is still a sequence, right? This is still all about just a list of ordered numbers. The pattern that the pattern that connects these together and makes them arithmetic is a little bit different than yesterday's, though. Okay, so instead of having a common ratio where we could divide the new term by the one right before it and find a common ratio that they're multiplying by, this is an additive, right, or an addition type of relationship. So in an arithmetic sequence, the difference between, instead of the ratio, it's the difference between each pair of consecutive terms is always the same. Okay, and that difference is what we call the common difference. So it's just the difference they have in common every time. What's the difference from 5 to 10? What's the difference from 10 to 15? From 15 to 20, and so forth. Okay, so each term is found by adding the common difference to the very previous term, and that lets you expand or extend the pattern in the sequence whenever you need to. Okay, so, we're not going to go too deep into the sequences. We've already introduced that. We're just going to look at the pattern and how we can use this equation to predict, right? So for the equation for arithmetic sequences, this is what it looks like. You're going to let n or an be any nth term in the arithmetic sequence that you might be interested in finding. And as long as you know what the first term in the sequence is and what that common difference is, that's all you need. Okay, just like before with the geometrics, basically you need to know what am I starting at and what is the pattern. Okay, so just a couple of reminders here, write these down. This right here represents the nth term in the sequence. So, and then once I have my equation set up, I could then use that to find any term I want. So once I have my nth term equation, I can then, instead of n, put in there, I want to know 75, and I could find the 75th term in the sequence, or 124, and I could find the 124th term in the sequence. You get the idea, right? So that's any nth term can always be found as long as you can identify the first term in the sequence, plus, and then they have the n minus 1 times d, where d is the common difference. Okay, that would be this here, with the value that you always get when you find the difference between the new and the previous term. Okay. Now, although this is the way that the book has it, you'll probably see me as we work through here put the D in front. For some reason, it just, I don't really know why they put the D behind the parentheses. It makes no mathematical difference at all. Okay, and I just like to have coefficients out in front of parentheses, but they works both ways. Now, there's one major thing that I want to emphasize that we didn't really talk about yesterday, since we were just introducing, we kept it slow. But these two equations that we came up with, the one for geometric sequences yesterday and this one, okay, this is what we call the explicit formula. So write that down. Okay, so this is the explicit formula for an arithmetic sequence, and yesterday's was the explicit formula for a geometric sequence. But it's called the explicit formula because it lets me find any term in the sequence, like way down the line. And the reason I'm starting to emphasize that is because after today's lesson, we're going to learn a different formula called the recursive formula, and it will have a recursive for the arithmetics and the geometrics. So in other words, an arithmetic sequence can be described by a formula or an explicit. And same thing with the geometric, it can be described with an explicit or a recursive. And the ones that you have learned so far, these are what we call the explicit formulas. Okay. The other big thing that I want to emphasize before we get started on some practice problems is that only for arithmetics, right? We didn't have to do this on geometrics yesterday, but only for arithmetics, after you have plugged in the first term and the common difference, we do go ahead and simplify, because these do simplify. The other ones yesterday did not. But explicit arithmetic formulas do simplify. So after you've inserted everything, we're actually not going to leave it looking like this. We'll distribute and combine like terms, and we'll clean it up. Okay? So the big thing here is make sure that after you have set up the explicit formula, this equation right here, or the explicit equation, then after that, make sure that you simplify it if possible. The geometric one did not simplify, but this one would. Okay. All right, let's go ahead and just get started in our practice. Those are the big things I want you to know, so you should have written that down. In 1 through 6, we just want to extend the next three terms in the arithmetic sequence. So they've already established it's arithmetic. We don't necessarily need to prove it. We just want to extend the pattern to the next three terms. Well, in order to do that, all I need to know is find what D is. What is a common difference? If I know that, then I can use it to extend on, further than the value they gave us. So very easy way to do that. Since I already know these are arithmetic, I can take any one of these and just find the difference. And just like we talked about, it's always toward the left. From right to left, you're doing new to previous, new to previous. So 8 minus 1, right? That would be one way to do this. It's like, oh, what's 8 minus 1? Well, that's 7. What's 15 minus 8? Oh, yes, that is also 7. And so forth. So it looks like our common difference for this one is 7. And then once we know that, then that lets us know, oh yeah, they're adding 7 every time. And you can test that. 1 plus 7 is 8. Yep. 8 plus 7 is 15. Absolutely. 15 plus 7 is 22. Looks good. And then we just continue the pattern to find the next three terms. So for this one, after 22, if I do 22 plus 7, I'll get 29. If I do 29 plus 7, I'll get 36. And if I get 36 plus 7, I'm going to end up with 43. Okay, so those would be the next three terms in the sequence for number 1. So that's just extending the pattern. If you already know that it is arithmetic, all you have to do is find the common difference and use it to continue the pattern going, basically, right? So let's try it on number 2. On number 2, let's find out what that common difference is. If I do 14 minus 20, that's a negative 6. So be careful with your signs. Okay, if I did instead 8 minus 14, I would still get a negative 6. And if I did 8 minus 2, I know I would get a negative 6. So for this one, my common difference is a negative 6. That's what they are adding every time. They're adding a negative 6 or combining with a negative 6. So if I continue that pattern, 2 and a negative 6 will be a negative 4. That would be the number that comes next. And then negative 4 and a negative 6 would then give me a negative 10. And a negative 10 and a negative 6 would give me a negative 16. So these would be the next three in that pattern. Okay. Let's try one more. Let's jump over here to number 6, and then you can definitely try these other ones and check them in a bit. On number 6, looks like our common difference is, let's see, 12, it seems. So, because I know that 14 minus 2, again, we're going in this direction. 14 minus 2 is 12, 26 minus 14 is 12, 38 minus 26 is 12, so it looks like our common difference is 12. And then we can use that to extend the pattern. So if I have 38 and I add 12, I'm going to get 50. If I do 50 plus 12, if I get 62 plus 12, that's going to be a 74. So this would be our next three terms. Okay, so those are pretty simple. I think you guys probably get the hang of that pretty quickly. Let's talk about graphing. Really similar to what we talked about yesterday. When we graph a sequence, we're going to essentially treat the x-axis, what I'm going to call n here, as the nth term, like the position in the sequence. So I'm going to kind of create a table here and say, okay, the first term was 1, the second term was 3, the third term was 5, the fourth term was 7, and so forth, right? And then the actual sequence value, a of n, that's going to be represented on my y-axis. So that's how I'm going to graph these. I notice these are all positive, so I just made this essentially a one quadrant type of thing. So let me go ahead and make my axes here. So on my x-axis is the n, the position in the sequence, and on my y-axis is the actual value. So n and a sub n. And then let's go ahead and plot our points. So if we graph this one right here, and I'm just going to go by ones, to be honest. Let's see. Maybe I'll just go 1, 2, 3, 4 right there. Okay. Since I only have to graph 4 terms. And then, but I am going up to 7. So here I'll go by ones. So 1, 2, 3, 4, 7, 8, and maybe 9 right there. Okay, so let's go ahead and graph them. So in the first position, the value was 1. Okay, so there's that 1, 1. Sometimes it helps to just see the ordered pair. In the second position, we had 3. So that's 2, 3. Okay, in the third position, it was 5. So third position, the number was 5. And in the fourth position, the number was 7. So in fourth position, the number was 7. Okay, and that would be the graph of this sequence. And if you notice, it does not have the curve that we had yesterday. And these are arithmetic. The patterning is addition. These guys make, I'm not going to connect it because it's a sequence, but it makes a straight line. So you could see the kind of the connection or the relevance there to the linears that we had been talking about for so long before we went to exponentials. Okay. Let's go ahead and do one more. So if we graph this guy right here, again, on my x-axis, I'm going to put the position of the value, or the position in the sequence. So first, second, third, fourth, and then a sub n will be the actual value. Like that. And again, at least the ones that we're plotting right now are all positive or 0. So I'm going to stick with this positive axis. And then let's go ahead and graph these. I think I'm going to do the same thing I did on the other one. I'm going to go by ones here. And I'll go by 2s here just because there's not that many. Okay. Okay, so in this sequence, in the first position, the value was 9. So in the first position, the value was 9. In the second position, the value was 6. In the third position, the value is 3. And in the fourth position, the value is right there at 0. So there's that sequence. That's all you have to do. And again, it's a sequence, it's exact numbers. We wouldn't connect those, but we definitely can see the relation or the correlation there to how these are similar to some of the linear stuff that we had done before. Okay. Number 9, don't let that intimidate you. You're really just still doing the same thing. You're graphing by position versus value. So n would still be the position. And then this would be the value. If this bugs you, change them to decimals. For graphing is one of really the few times that I can concur that the decimals might be easier. So if you want to say, I know that 15 divided by 2 is really 7.5, that 13 divided by 2 is really 6.5, that 11 divided by 2 is really 5.5, that 9 divided by 2 is really 4.5, you can see that this is really it's very harmless, right? It's just harmless. And then you could just graph it the same way. So if you want to do that one, you can do that one for practice. Go ahead and try it and then press play and check your work. Okay, so on these, I went ahead and I finished out all the ones that we hadn't done. And if you wanted to check, so if you tried 3, 4, or 5, they're in orange up here. There's your common difference and the next three values, the common difference and the next three values, the common difference and the next three values. So you can check those. And then coming back to where we left off on number 9, this would be what those points would look like. I spread this out, just like we did in the previous ones, every other one on my scaling. This one went, by ones, and then it would just be those 4 points right there. So if this looks, similar to what you've got on your page, then it looks like you are in good shape for arithmetic sequences. So you understand the pattern, and we're ready to go. So these are just those. You can utilize the ones in the back as extra practice if you'd like. I'm going to jump down to determining if something is arithmetic. So this is now on the back page, right? You can use these as extra practice. And then let's talk about determining if something is representative of arithmetic, and also using the nth term formula, which is at the bottom there. So we'll finish out with that. Okay, so I'm going to move this up. Look at those guys there. From graphs, and we talked a little bit about this, I guess I talked with the specific students. Sometimes on the graphs, some students are okay with it. Some students really find it hard to kind of see the patterns. Feel 100% comfortable taking the data from the graph and taking it back to a sequence. So just kind of like doing the reverse of this, right? Where here we had a sequence and we created the graph. Now they're giving you a graph. If it's easier for you to look at that sequence in the listed form, feel free to do that, okay? So let's practice doing that on number 13. On number 13, when they give us this graph right here, and they tell us it's a sequence and we want to determine if it's arithmetic, if it makes it easier, let's go ahead and list this out. Because what this tells me is, remember, the x-axis is the position, and then the y-axis is the term. So what that ordered pair right there is telling me is that the first term in the sequence is 0. So I could list that out and say, okay, my sequence is 0, comma. That the second term is 1. So the second term in the sequence is 1. That the third term is 4. So the third term is a 4, and that the fourth term is a 9, okay? So if you want to write it like that, feel free to do that. It's the same information. The first term was 0, the second term was 1, the third term was 4, and the fourth term was 9. That's the sequence that graph represents. And then we could do our test, right? Well, if this is arithmetic, which is what they're asking me about, then I should find a common difference when I subtract or find the difference of 1 minus 0. Well, that's 1. And then when I do 4 minus 1, well, that's 3. So that's not a common difference. They don't have that in common, right? And if I try the next one, 9 minus 4, that's 5. There is not a common difference. The difference changes. The difference changes every time. I have a difference of 1, then I have a difference of 3. Is there a pattern? Sure, but that's not what we're asking. We're asking is this arithmetic? And with that evidence in hand, we can very decisively say, no, this is not. Okay, and how do we explain it? Well, we have our work shown right here. Okay, the difference is not a common difference, or there is no common difference. No common difference, at least not on number 13. Okay, and that's basically what you would be looking for. And something else that you could do is look to see, if the sequence looks like it's graphing out to a path that would make a straight line, that's probably a good candidate for something that is arithmetic. Okay, but let's try it out. Don't take my word for it. let's work it out. So again, you can look at it from here and catch a pattern there, or you could write the sequence. The first term in this sequence was 20. Then the second term was 30. The third term was 40, and the fourth term, was 50. And when I test whether or not this has a common difference in this direction, 30 minus 20 is 10. Okay, 40 minus 30 is also 10. 50 minus 40 is 10. I'm showing that difference in different ways, so you can decide which one you like better. Either way, this does have that common difference. Okay, so the difference between my values is the same every time. It's always a difference of 10. That means it's going up by 10, right? So I could answer this question with a very comfortable yes on this one. and the common difference is 10. Okay, all right. And you could do the same for number 15. I'm going to jump over, if it's okay, to actually using our equation, especially because I want to practice the simplifying piece, which is a little bit different than before. Okay, so this is where it says write an equation for the nth term. This is where this guy is going to come in. We're going to write the equation for the nth term, and then we're going to use it to find the 10th term after that. So it's kind of a part A, part B. Like yesterday, first we'll write what it is for any nth term, and then we'll solve it for when n is 10. Okay, so on number 16, let's go ahead and get started. The first things that I need to be able to do before we proceed is identify the ingredients I need, which is what is the first term. So for this one, I need what is the first term and what is the common difference. The first term's easy, right? I can tell right away here that it is negative 5.4. Okay. The common difference is whatever this difference is. So if I do, and here you're welcome to grab this and do that. So if I do negative 6.6 minus a negative 5.4, oh, what did I do wrong? Oh, that should be a decimal. Okay, that looks like our difference is a negative 1.2. And you could test that for any of the other ones, but that's our common difference, is a negative 1.2. So then let's talk about writing that equation. So just as a refresher, the equation for arithmetic sequences, that explicit one we talked about earlier, looks like this. And then plus, and I like putting the D in front, but it doesn't matter. Okay, you could put it either way. But it's the first term plus the common difference times that parentheses. Okay, and so let's go ahead and fill that in. For this one in particular, that would be the nth term would be that first value, and then the common difference times n minus 1. Okay, now yesterday we would have stopped there. However, that's what's a little bit different here. This simplifies. We can do a little bit of work here and clean this up and make it easier to look at. And you will be expected to do that to get credit. So now that we have set up the equation, I can distribute this and maybe probably combine some like terms before we can finalize our equation. Okay, so first let's distribute. So I will leave this guy alone. Negative 1.2 times n is negative 1.2n. And then negative 1.2 minus n times a negative 1 is a positive 1.2, sorry. Okay, so I'm just distributing into the parentheses this d value. So d times n is right here, and then d times the negative 1 gives me that. And then pretty much always what will happen is that these guys are like terms and you'll be able to combine them. Okay, and so when this is all said and done, our simplified best version of this is negative 1.2n, and then when I combine that negative 5.4 and that positive 1.2, I should get a negative 4.2, and that's a minus, and that is the formula or the equation. Okay. For part B of this is solve for the 10th term in the sequence, right? So now I can take this, plug in a 10 here and here, and solve it. And I know, man, we need more room in this. I need to make myself a note that we need more room in these notes. But basically all I have to do to evaluate this is plug in a 10 for n. So I've got negative 1.2. I'm going to insert a 10 as my input, minus that 4.2. So apparently the 10th term in my sequence is negative 16.2. Okay, so negative 16.2. There it is. Okay, so that was the nth term equation, and then this is the actual 10th term after we've used that equation. Let's try it again on number 17. So on number 17, first of all, let's identify our first term in the sequence, which is the 43. And let's identify our common difference. If we're going 43, 38, 33, 28, that's a decrease of 5. Or a common difference of negative 5, if you will. Okay, so let's lay that out. If we write this equation with those two ingredients in there, then our equation would be a sub n We're starting at 43, and then our common difference is a -5, and we'll do that -5 times that n minus 1. But because this is an arithmetic and it can be simplified, you're expected to distribute that -5. -5 times n is -5n. And -5 times -1 is a +5. And then these guys will be like terms, so you'll be able to combine those. And our resulting equation will be that -5n and a 48. And if this looks a little bit like y equals mx plus b, you are not wrong. That's why it graphs in a straight path. This has a lot of similarities to linear functions, although it's not the same. Okay, it's very similar. Okay. So once we know this, we can use it to find the 10th term by just plugging in a 10 and evaluating this, right? So once we have this guy, we can say, okay, our function is -5. I'm going to look for the 10th term in the sequence. I'm going to add that 48. So -2 would be the 10th term in that sequence. And that's the second thing they were asking for. All right, so I want you to pause it and try these next 4 and then press play and to see how you did. Okay, so check your answers now and see if you were able to get that arithmetic sequence equation, what we call the explicit formula or the explicit equation, correctly, even after simplifying. So this is the final fully simplified nth term equation here for each one of these. And then the 10th term, when we insert a 10 and solve that, this is the 10th term in each of those sequences. So check those out and see how you did on those. And if those feel good, let's finish out with the word problem. And we'll end on this right here. So it says in an auditorium, the first row of seats has 30 seats. So this is what we're starting with, is a row of 30. Each row behind the first row has 4 more seats than the row in front of it. Okay, so if I thought of this as a sequence, like we've thought about, like, okay, so that means the first row has 30, and then every row after that has 3 more, so maybe the next row would then have 34, then the next row would have 38, then the next row would have 42, and so forth and so forth. So that seems to be the pattern. And what they want to know is how many seats would be in the 25th row. So this is first row, second, third, fourth, all the way down, and they're asking for that 25th. This is an excellent example of where we would not want to have, just try to extend this 25 values. This is not the idea here at all. The idea is to then come up with an explicit formula that we can use. So let's do that. So it looks like that 30 right there, that's our a sub 1. That is our first term. That is the first value in our sequence. It's how many seats the first row has. And then that 4 is our common difference. It's basically every row has 4 more than the previous, so that's the common difference between our values in the little sequence we created. So let's then take that, and since this is our equation, at least our starting equation, we'll fill in what we know. So I can find any nth row as long as I know that I started with 30 and that I'm going to add 4 every time n minus 1 times. And then we'll simplify this. So we'll distribute that 4. So it'll be 4n minus 4. And then we'll combine like terms. So the explicit formula that can help us solve this problem is this guy right here. Okay, it's 4n plus 26, sorry. Okay, and so since we know that, we can now use that to find the 25th row, or how many seats there are in the 25th row, because I know all I have to do is do 4 times that 25 plus the 26. Okay, well, I know that 4 times 25 is 100, and 100 plus 26 is 126. So the has 126 seats. That's a big auditorium. Okay, so there's our answer. That's an example of how you would use it. All right. So if that feels comfortable, that is all about arithmetic sequences. And the two formulas that we've been using, those are called the explicit formulas. We'll get to mess around with some recursive ones next.